At the end of this video, you should be able to identify several forms of energy, calculate kinetic energy for an object, apply the work kinetic energy theorem to solve problems, distinguish between kinetic and potential energy, classify different types of potential energy, and calculate the potential energy associated with an object's position. Chapter 5, Section 2, Energy. Kinetic. Chapter 5, Section 2, Energy. Kinetic energy. Kinetic energy is energy associated with an object in motion. Figure 2.1 on the screen here shows a cart of mass m moving to the right on a frictionless air track under the action of a constant net force, F, acting to the right. Because the force is constant, we know from Newton's second law that the cart moves with a constant acceleration, a. While the force is applied, the cart accelerates from an initial velocity, v sub I, to a final velocity, v sub f. If the cart is displaced a distance of delta x, the work done by F during this displacement is equal to force times delta x, which is equal to the mass of the object times the acceleration times the displacement, ma delta x. When you studied one-dimensional motion, you learned that the following relationship holds when the object undergoes constant acceleration. Final velocity squared is equal to initial velocity squared plus 2a delta x, which can be rearranged to solve for acceleration times displacement, which is equal to final velocity squared minus initial velocity squared divided by 2. Substituting this result into the equation net work is equal to ma delta x gives net work is equal to m multiplied by quantity vf squared minus vi squared divided by 2, which can be rearranged as net work is equal to 1/2 mvf squared minus 1/2 mvi squared. The quantity half mv squared has a special name in physics, kinetic energy. The kinetic energy of an object with mass m and speed v, when treated as a particle, is given by the expression shown on the screen here. Kinetic energy is a scalar quantity, and the SI unit for kinetic energy, and all other forms of energy, is the joule. Recall that a joule is also used as the basic unit for work. Kinetic energy depends on both an object's speed and its mass. If a bowling ball and a volleyball are traveling at the same speed, which do you think has more kinetic energy? You may think that because they are moving with identical speeds, they have exactly the same kinetic energy. However, the bowling ball has more kinetic energy than the volleyball traveling at the same speed because the bowling ball has more mass than the volleyball.
Kinetic energy is energy of motion. Both of these cars are moving, so they both have kinetic energy. Kinetic energy depends on both the velocity of an object and its mass. Kinetic energy is calculated by multiplying mass by velocity squared and dividing by 2. If the red and green car each have the same mass, the red car has more kinetic energy because it is moving faster. Even though the truck and the red car both have the same velocity, the truck has more kinetic energy because it has more mass.
The net work done on a body equals its change in kinetic energy. The equation net force is equal to 1/2 mass times final velocity squared minus 1/2 mass times initial velocity squared, derived at the beginning of this section, says that the net work done by a net force acting on an object is equal to the change in the kinetic energy of the object. This important relationship, known as the work kinetic energy theorem, is often written as shown on the screen here. Net work is equal to change in kinetic energy, or W sub net is equal to delta KE, kinetic energy. When you use this theorem, you must include all the forces that do work on the object in calculating the net work done. From this theorem, we see that the speed of an object increases if the net work done on it is positive, because the final kinetic energy is greater than the initial kinetic energy. The object's speed decreases if the net work is negative, because the final kinetic energy is less than the initial kinetic energy. The work kinetic energy theorem allows us to think of kinetic energy as the work that an object can do while the object changes speed, or as the amount of energy stored in the motion of the object. For example, the moving hammer in the Ring the Bell game in figure 2.2 on the screen here has a kinetic energy and can therefore do work on the puck. The puck can do work against gravity by moving up and striking the bell. When the bell is struck, part of the energy is converted into sound.
The net work done on a moving object is equal to the change in its kinetic energy. For example, a hammer can be used to drive a nail into a piece of wood. The hammer has a certain kinetic energy as it begins to strike, and a different kinetic energy when it comes to rest against the nail. The difference in the two kinetic energies is equal to the work done on the hammer by the nail. The kinetic energy of an object can therefore be thought of as the work it can do or can have done on it, if the mass or the velocity of the object changes. Because the force on the hammer by the nail is opposite the displacement of the hammer, the work done on the hammer is negative. However, the work done by the hammer on the nail is positive, because the force of the hammer on the nail and the displacement of the nail are in the same direction. The kinetic energy of an object can be thought of as the work it can do as it comes to rest.
Potential energy. Consider this balanced boulder shown in figure 2.3 on the screen here. As long as the boulder remains balanced, it has no kinetic energy. If it becomes unbalanced, it will fall vertically to the desert floor and will gain kinetic energy as it falls. What is the origin of this kinetic energy? Potential energy is stored energy. Potential energy is associated with an object that has the potential to move because of its position relative to some other location. Unlike kinetic energy, potential energy depends not only on the properties of an object, but also on the object's interactions with its environment. Gravitational potential energy depends on height from a zero level. You learned earlier how gravitational forces influence the motion of a projectile. If an object is thrown up in the air, the force of gravity will eventually cause the object to fall back down. Similarly, the force of gravity will cause the unbalanced boulder in the previous example to fall. The energy associated with the object due to the object's position relative to the gravitational source is called gravitational potential energy. Imagine an egg falling off a table. As it falls, it gains kinetic energy. Where does the egg's kinetic energy come from? It comes from the gravitational potential energy that is associated with the egg's initial position on the table relative to the floor. Gravitational potential energy can be determined using the following equation. PEG, potential energy due to gravity, is equal to mgh, which is to say gravitational potential energy is equal to mass times free fall acceleration times height. The SI unit for gravitational potential energy, like for that of kinetic energy, is the joule. Note that the definition for gravitational potential energy given here is valid only when the free fall acceleration is constant over the entire height, such as at the point near Earth's surface. Furthermore, gravitational potential energy depends on both the height and the free fall acceleration, neither of which is a property of the object. Also note that the height, h, is measured from an arbitrary zero level. In the example of the egg, if the floor is the zero level, then h is the height from the table, and mgh is the gravitational potential energy relative to the floor. Alternatively, if the table is the zero level, then h is zero. Thus, the potential energy associated with the egg relative to the table is zero. Suppose you drop a volleyball from a second floor roof and it lands on the first floor roof of an adjacent building. See figure 2.4 on the screen here. If the height is measured from the ground, the gravitational potential energy is not zero because the ball is still above the ground. But if the height is measured from the first floor roof, the potential energy is zero when the ball lands on the roof. Gravitational potential energy is associated with an object's position, so it must be measured relative to some zero level. The zero level is the vertical coordinate at which gravitational potential energy is defined to be zero. This zero level is arbitrary, and it is chosen to make a specific problem easier to solve. In many cases, the statement of the problem suggests what to use as the zero level.
Potential energy is sometimes known as energy of position or stored energy. One form of potential energy is gravitational potential energy. An object that is raised above ground level has work done on it. This work increases its energy. At the top of the slope, the ball is not moving, but it has the potential to do so. If it falls, the gravitational potential energy will change to kinetic energy. There are many other forms of potential energy. A piece of wood, for example, contains chemical potential energy that can be converted into heat and light when it burns. Increasing pressure along a fault line does work on the various rock layers and increases the potential energy along the line. This energy is released during an earthquake.
Elastic potential energy depends on distance compressed or stretched. Imagine you are playing with a spring on a tabletop. You push a block into the spring, compressing the spring, and then release the block. The block slides across the tabletop. The kinetic energy of the block came from the stored energy in the compressed spring. This potential energy is called elastic potential energy. Elastic potential energy is stored in any compressed or stretched object, such as a spring or the stretched strings of a tennis racket or a guitar. The length of a spring when no external forces are acting on it is called the relaxed length of the spring. When an external force compresses or stretches the spring, elastic potential energy is stored in the spring. The amount of energy depends on the distance the spring is compressed or stretched from its relaxed length, as in figure 2.5 on the screen here. Elastic potential energy can be determined using the following equation. Elastic potential energy is equal to 1/2 the spring constant times the distance compressed or stretched squared. The symbol K is called the spring constant or force constant. For a flexible spring, the spring constant is small, whereas for a stiff spring, the spring constant is large. Spring constants have units of newtons divided by meters. This is N/m.
The spring constant determines how much force a spring will exert for a given compression or expansion. For example, if we attach 1 kilogram weights to each of these springs, we see that they stretch different amounts. The larger the spring constant, the stiffer the spring, and the more force that is required to stretch it. The spring constant depends on the type and amount of material a spring is made of, and how the spring is formed.
At this point, you should be able to identify several forms of energy, calculate kinetic energy for an object, apply the work kinetic energy theorem to solve problems, distinguish between kinetic and potential energy, classify different types of potential energy, and calculate the potential energy associated with an object's position.